Thank you, Andy. My name is Brad Mosher, and I'll be discussing fault tolerance services. Fault tolerant services are available even with processes failing by replicating data and functionality at replica managers. A service is considered correct if it keeps responding despite failures and if clients cannot tell the difference between a service they obtain from an implementation with replicated data and one provided by a single correct replica manager. However, care is needed in meeting these criteria, and if precautions are not taken, then anomalies can arise when there are several replica managers. There are a few key terms to understand before considering models of replication for fault tolerance. These terms include linearizability and sequential consistency. A replicated shared object service is said to be linearizable if for any execution there is some interleaving of the series of operations issued by all the clients that satisfies the following two criteria. First, the interleaved sequence of operations meets the specification of a single correct copy of the objects. Second, the order of operation is in the interleaving is consistent with the real times at which the operations occurred in the actual execution. It should be noted that linearizability concerns only the interleaving of individual operations and is not intended to be transactional. A linearizable execution may break application-specific notions of consistency if concurrency control is not applied. Real-time in this definition does raise the issue of practicality of linearizability, since we cannot synchronize clocks to the required degree of accuracy. Sequentially consistent replicated shared objects share much of the same criteria as linearizability in that the interleave sequence of operations meets the specification of a single correct copy of the objects. However, where they differ is the order of operations. With sequential consistency, the order of operations in the interleaving is consistent with the program order in which each individual client executed them. Absolute time and total order of operations is not required in the sequential consistency definition. The only important idea of ordering that is relevant is the order of events at each separate client. The interleaving of operations can shuffle the sequence of operations from a set of clients in any order, as long as each client's order is not violated and the result of each operation is consistent. This leads us to passive or primary backup model of replication for fault tolerance. In this model, there is at any one time a single replica manager and one or more secondary replica managers. The front ends communicate only with the primary replica manager to obtain the service. The primary replica manager executes the operations and sends copies of the updated data to the backups. If the primary fails, one of the backups is promoted and acts as the primary. The sequence of events when a client requests an operation to be performed is as follows. The front end issues the request containing a unique identifier to the primary replica manager. The primary takes each request atomically in the order which it receives it. It checks the unique identifier in case it has already executed the request, and if so, it simply resends the response. Primary executes the request and stores the response. If the request is an update, then the primary sends the update state, the response, and the unique identifier to all the backups. The backups send an acknowledgement. The primary responds to the front end, which hands the response to the client. In the active model of replication for fault tolerance, the replica managers are state machines that play equivalent roles and are organized as a group. The front ends multicast their requests to the group of replica managers, and all the replica managers process the requests independently but identically and reply. If any replica manager crashes, this need have no impact upon the performance of the service since the remaining replica managers continue to respond in the normal way. The sequence of events when a client requests an operation to be performed is as follows. The front end attaches a unique identifier to the request and multicasts it to the group of replica managers using a totally ordered, reliable multicast primitive. The front end is assumed to fail by crashing at worst. It does not issue the next request until it has received a response. The group communication system delivers the request to every correct replica manager in the same total order. Every replica manager executes the request. Since they are state machines and since requests are delivered in the same total order, correct replica managers all process the request identically. The response contains the client's unique request identifier. No agreement phase is needed because of the multicast deliver semantics. Each replica manager sends its response to the front end. The number of replies that the front end collects depends upon the failure assumptions in the multicast algorithm.